right, guys, let's get started. I'm very excited because my arrow on the screen is now bigger this week, so that is a major upgrade. Okay, so let's look a little bit at dive planning this week. So we're going to look at compartments, half times, Mvalues, the difference between the RDP, which we use in PADI, versus some of the older US Navy tables. We're going to look at the theory behind some of the dive computers we're using now, and then some rules for using the RDP that we need to actually apply to our computer diving as well. All right, so all of this decompression theory is mainly based off of what we call the Haldane Model, which was invented by John Scott Haldane. He basically just experimented on goats. This goat here has actually been experimented on, and that's why its leg is all weird, because it has decompression sickness. And he basically came up with the ideas of theoretical tissues and half times that are going to be common to almost all decompression models. And he first published his findings in 1908. So the ideas of decompression theory actually predate modern scuba equipment, which wasn't until Cousteau in the 40s. But there were, mostly for military and construction purposes, there were divers with surface supply air that were going down and experiencing decompression sickness. So the research was being done for them. And the basic idea with compartments is that different pieces of our body absorb and release nitrogen at different speeds. Things like blood and fat are going to absorb nitrogen easier and faster than things like muscle and bone do. And because of these different tissues, our decompression model has what we call theoretical tissues or compartments. And those are ways to measure how fast or slow our body is absorbing and releasing nitrogen. So a fast compartment is just anything that absorbs and releases nitrogen quickly, and a slow compartment would obviously be the opposite of that. Now, each one of these theoretical compartments has a half time, which is a measure of how quickly it absorbs and releases nitrogen. And a half time is the time in minutes for a compartment to go halfway from its beginning tissue pressure to full. So that doesn't mean that it'll go 0 to 50, then 50 to 100. It's not a linear progression like that. As we actually increase the amount of absorption, it's a smaller and smaller and smaller amount that's absorbed each time. And the unit we use to measure tissue pressure is meters of seawater. And with modern models, so that's typically in between 300 to 600 minutes. Now, the reason I've listed 6 half times here is because after 6 half times, we basically call it done and we call it full. So once it hits 98.4%, we're going to consider that that compartment is full. This little black piece left here, it's just going to keep being half and half and half and half and half of that tiny little bit at the end, and it's going to be splitting hairs and never actually fully reach a complete 100%. So after 6 half times, we call it full. So for example, if we had a 5-minute halftime compartment, what's the tissue pressure? Going to be 5 minutes after in 18 meters of seawater. So after 5 minutes, the compartment will be half full if it is a 5-minute halftime compartment. And if it is an 18-meter compartment, that is half full. Half of 18 is 9. So our answer would be 9 meters of seawater is how full that compartment is. After 10 minutes, we'd be at 13.5. That would be 75% of 18. And as we mentioned, after 6 half times, we consider a compartment to be full. So in this case, if it is a 5-minute compartment, 6 times 5 is 30 minutes to fill this compartment. Okay. Now, the faster the compartment, so if it has a shorter half time, the higher the M value, the more nitrogen is allowed to have when surfacing. The slower the compartment, the lower the M value is. And the M value is basically just the maximum amount of nitrogen that's allowed to be left in it after a dive. And that is a theoretically safe pressure of nitrogen within a tissue that if we're ascending at 18 meters per minute or slower, there won't be any massive risk of DCS. And the compartment that reaches M value first is called the controlling department. So this is why deeper dives are going to have shorter limits than shallower dives. Now, looking at the RDP, which we use with PADI, and the US Navy tables. So the recreational dive planner has 14 of these theoretical tissues or compartments, and they have a 60-minute surface credit. So they're going to have a faster gas washout. Whereas the US Navy tables only had 6 compartments with 120-minute surface credit. So they release that gas slower. Now, the way I'll remember this one is basically just the US Navy tables were invented for Navy divers who at the time were all, 20-something American men. So they all look the same, only about 6. Whereas the RDP is built for recreational diving, which has a much wider scope of people engaging in it. So there's many more compartments for that. With the RDP, theoretically within 6 hours, your body should be completely clear of nitrogen, whereas with the US Navy, it would be about 12 hours. And you can see the difference here. So the RDP is really meant for several dives in a day, right? If you're going out diving, you might be doing 3, 4, 5 dives in a day recreationally. So the limits are sometimes a bit shorter, but you're doing more diving. Whereas the US Navy table is looking at, specific single objective-based dive, maybe staying a little bit longer, but then spending much more time on the surface, allowing that nitrogen to safely leave their bodies. And the reason we still talk about these US Navy tables is because at one time they were kind of the thing within scuba diving. And this RDP didn't come around until the late 80s. So before we had computers, we were using this mainly the US Navy tables. And it's difficult to make your own table and do all the research. So there wasn't really a big push from anyone to make an external dive table for recreational diving. A lot of divers in the early days of scuba diving were coming out of the Navy anyway. The US Navy tables were available to people, and though they're not built for recreational diving, they were working pretty well as long as everyone was following conservative diving practices. And it wasn't until 87, 88 when PADI Divemaster Raymond Rogers was working at DSAT, and he actually came up with this RDP that we use today for recreational dive planning. Now, with dive computers, there's a couple advantages that we're going to get from them. A lot of the time, it seems like we're getting longer dives using a computer than if we were doing our calculations with a dive table. And that's basically because it's calculating the dive exactly. It's an up-to-date multi-level profile. And it's going to eliminate any of the rounding that we might have to do if we use a dive table where they don't have every meter or every time, and you're rounding to a more conservative factor sometimes. So with dive computers, they'll often use Spencer limits, which are similar to the RDP. These ones aren't as common anymore. We'll look at what the more modern computer algorithms are. So with the Spencer limits, all the compartments with 60-minute or faster half times wash down at that 60-minute rate, whereas any slower compartments wash out at their underwater halftime rate, just like the RDP table does. Then there's also this thing, which is the EE washout, which is exponential uptake and exponential release. So all the compartments are going to wash out at that halftime rate that we were looking at before. And this means that the really, really fast compartments that control deeper dives can completely unload their nitrogen quickly. So we could do dive profiles with this EE washout that maybe aren't demonstrated to be super reliable. The table wouldn't recommend us doing it, but the computer wouldn't stop you from doing it because the algorithms would allow it. Now, what is used commonly today, almost any dive computer that you're going to buy is going to be based loosely on either the Bowman limits or the RGBM model. There's a lot of different proprietary names for the actual models. For example, Aqualung uses the pelagic model. This is just Bowman limits with a slight twist. The basis is nearly identical within a lot of them. And the idea with this is the compartments release nitrogen at their underwater halftime rate, but the actual single dives are going to be a little bit shorter than the RDP. You may, for example, 18 meters, the limit on an RDP is 56 minutes. If I go into my Sunto, which uses an RGBM model, that limit's actually only going to be 51 minutes. So there is a bit more conservatism baked into these newer models. They also have much slower ascent rates. Things with Bowman limits will often use a variable ascent rate. So actually, depending on how deep you are when you're ascending, the computer might insist you go slower than at other depths. With the RGBM models, which are your Cressis, your Maras, your Suntos, they normally have a maximum ascent rate of 10 meters per minute. So there is a lot more conservatism within the newer models based on findings and updates that are happening in the dive industry. This is kind of an overview of a lot of the common dive computers out there. You can see the number of tissue groups being used, the range of half times that they're using in their compartment, the type of ascent rate, and the decompression model that they're using. So you can see there's quite a few using variations of the RGBM. Anything where you see ZH, that's going to be tied towards the Bowman stuff. Z is for Zurich. Bowman was a Swiss doctor. So that's where that one comes from. Now we'll have a look at some of the rules that were made originally for the RDP table that are still super important for us to know when diving with our dive computers. It's something I kind of strongly stress within my professional candidates is we can't just kind of strap a computer to our wrist, jump in and just follow it. We should be doing that a little bit of pre-planning beforehand and keeping in mind some of the recommendations from earlier table diving. And so first of all, when we do a dive with a table, as we saw, the US Navy table and the RDP table both have pressure groups that use letters of the alphabet. We can't move from one table to the other, okay? They're different designs, we can't do that. Within any RDP product, though, you can do that. So if you planned an air dive with an RDP table and then wanted to move on to a nitrox dive, you could directly do the calculations and switch over to an RDP nitrox table. The common ones you get are the 32%, the 36% tables. I've never had the pleasure of using one, but even if you manage to find one of the old wheels, you could actually cross-reference pressure groups between that and an RDP table. Some more general rules. When we are doing dives in cold water or under conditions that are going to be strenuous, if we're maybe doing some search and recovery or something like that, or swimming in some very hard currents, we want to plan the dive as though the depth is 4 meters deeper than actual, okay? Now, this is one that we should be keeping in mind, right? Unless you have a very advanced dive computer, it's not taking into account the actual water temperature or how much sort of strenuous activity you're doing. There are some new ones I've seen with Scuba Pro that actually do calculate your heart rate and factor that into the algorithm, which is really cool. But if we are doing cold water diving, we actually would want to keep this in mind and be more conservative with our dive profile. You know, we know as responsible divers, we don't dive right to the limit, but we might want to be even more conservative with how close we're approaching our NDLs if we're diving in cold water. This next point is important for any exams you might do at the dive master or instructor level. They'll often give you multiple dive profiles, and they'll ask you to do a calculation where your first step is to put them in the correct order. So if you ever see a question like that, they're just asking you to put them from the deepest dive first to the shallowest at the end. Now, doing the opposite of that is referred to as reverse profiling. There has been some new research on that recently. If you're interested, I can send it to you guys, released by Dan Europe, that suggests that there might be not maybe an increased risk of DCS if you do reverse profile and if you follow conservative factors, but it is a general rule that still exists and we should be aware of it. And it is better for dive planning anyway. Going deeper to shallower, you're going to have longer NDLs on your subsequent dives, planning that way, which is, you know, safer to do anyway. We need to keep in mind our maximum depth. Okay, DSD is 12 meters, open water 18, 30 meters, and then 40 if we have done our full PADI Deep specialty course. And the reason that the 42 meters exists on the RDP, which is obviously beyond recreational limits, is just for emergency planning. When we're doing more dives in a day, if we're doing it with a table, we have the Wxyz Rule, where if we can see down at the bottom here, if we're ending any of our dives within the WRX group, we should be waiting at least an hour on the surface, or if we're in Y or Z, we should be waiting at least 3 hours on the surface before we go back in again. Now, your computer wouldn't stop you getting back in the water. There's some that have icons and warnings. Maybe it's not the best time for you to go diving again just yet, but it would let you back in, and it would let you, it would calculate a dive profile for you. Now, these are quite large numbers down here, but something like that 3-hour interval, 98 minutes, about an hour and a half at 14 meters is not necessarily impossible, right? If we're doing quite shallow shore diving, maybe doing some data collection or a shore cleanup dive or something like that, with decent air consumption, we could be actually approaching that limit. And that's when we'd be hitting very close to the maximum that our slow tissues could handle in terms of nitrogen absorption. So, you know, planning things like that. 56 minutes at 18 meters. We're going near our limits at 18 meters. We should be at least an hour surface interval after that. And actually, you know, being aware of that when we're planning our surface intervals if we're doing like a 2-dive boat or something like that. Making a safety stop for 3 minutes at 5 meters after every dive. This is the recommendation. We must make a safety stop anytime we go 30 meters or deeper. If we are 3 pressure groups from our NDL, or if we are at the limit. So if we go back for a second, anything gray or black, okay, is a mandatory safety stop. We should still do one on any dive, but if you haven't really gone so close to your limits or anything like that, and if there is any sort of emergency, you're not putting yourself at too much risk. If you do omit it, it might be the safer option to actually, you know, get back to the surface sooner rather than later, right? Now, if we do accidentally go beyond our no decompression limits, we've got a couple rules. If we've gone over our limits by 0 to 5 minutes, we want to do at least an 8-minute emergency decompression stop. If we've exceeded our limits by more than 5 minutes, we'd want to do at least 15 minutes. Now, this is why we stress the importance of having a drop tank available to us when we're doing deep dives. It's not because if we run out of air, we're going to be able to breathe off this thing. It's with deeper diving, there's obviously a higher likelihood of us surpassing our no decompression limits and needing to do the emergency deco stop. And if, say, we were doing a 15-minute stop, we probably haven't done gas planning that we're going to have that much reserve available to us. So that's why we do stress the need for drop tanks on all of our deep dives, just in case we do need to be making these stops. Now, if we miss a deco stop, or we're running out of air, we would obviously surface and exit the water. We want to stay under the water for at least 24 hours and breathe pure oxygen if it's available, and then of course monitor yourself for any signs or symptoms of DCS that might appear. And if we do any altitude diving, the RDP is calculated assuming that we're going to surface at sea level. So if we're surfacing up a mountain somewhere, if we're diving in lakes in, I don't know, the Alps or something like that, we don't have a full atmosphere of pressure on our head when we reach the surface. So nitrogen could come out of our tissues at a quicker rate than we were hoping. So we do need to make an adjustment to our dive profile anytime we're diving 300 meters above sea level or greater. And if we look at this chart here, we're going to have shallower maximum depth, and we're going to calculate the dive much deeper. Most modern dive computers do have altitude settings built into them, but we need to be aware and we need to make those adjustments before doing these dives. If we're diving 3,000 meters above sea level, the actual deepest we could go would be 28 meters. And that would be as if we were diving at 39 meters normally. So very different limits we're going to be looking at there, shorter dive times, shallower dives as well. And it's actually going to affect your safety stop depth as well. We're aiming for 5 meters, so typically between 4 and 6. If we were at an altitude of up to 3,000 meters, we'd actually be aiming for only about 3 meters depth on that safety stop. And our last rule is the fly before diving rule of 12 hours if you've done a single dive, or 18 hours before flying if you've done multiple days of diving or multiple dives in a single day. Most dive computers nowadays will have an icon of a little airplane on them, letting you know if by their calculations it's safe for you to fly or not. But obviously, if we have students or fun diving customers that are renting computers from us, they're not going to have that little icon available to them. So they need to know the RDP rule of 12 hours and 18 hours, and we need to make sure that we're communicating that to all our students to keep them safe as well. Cool. So that was a look at some of the theory behind dive planning and the models that we use, compartments, half times, Mvalues, some of the history with the US Navy tables, what's going on with our computers, and the RDP rules that we need to apply when using our computers. So if you have any other questions, please find me on Facebook or Instagram, send me an email. We are going to continue these Thursday sessions going into next month. We're going to have some new topics available. If any of you guys have a topic that you would like discussed, please let me know. I'm happy to talk about just about any topic in diving, whether that is something to do with marine life or getting more into the theoretical side of things like we've been doing over the past month. So thank you to everyone who joined in. I've really appreciated your support, and I'll see you guys next week.